Hi everybody, we are in section 12.3, so we're talking about linear regression, and in this section we're going to be looking at the actual regression equation, so we can actually create this line of best fit for our data. So we are going to be referring back, if you just look back at the last section, just a couple pages back here, this data set, so this is example 12.4, so the depth at which drilling begins, so drilling into rock, and then the time that it takes to drill. This data here is what we're going to be talking about and referring to throughout the next couple of sections. So when it refers to example 12.4, this is what it's talking about. Okay, so we already saw this data, and we already created a scatter plot last time for this data. So this is what it's referring to. Alright, so let's go ahead and get into this new section here. So the least squares regression line, also known as the line of best fit, is the line that minimizes the sum of the squared errors. We represent this line as, this is y hat equals b1x plus b0, where b1 is the slope and b0 is the y-intercept. Okay. So when we're dealing with these values, these aren't something we're going to be computing by hand very much. We're just going to be using technology. Particularly Desmos is very good at doing these linear regression lines. So, but basically we're just trying to find a line that best fits the data. So if you have a bunch of data points that seem to have a linear relationship to them, can we find the line that best and most closely matches and fits that data? Okay. Alright, so use the data from example 12.4, find the least squares regression line, and draw this line on the scatter diagram of the data. Okay, so let's switch over to Desmos here. And you might want to have Desmos out if you want to try this on your own, just so you know how to do this. But basically, if you want to create a least squares regression line, so you can kind of ignore all the stuff I have going on over here for the time being, you go to this plus button up here in the upper left corner, and you're going to open a table. Okay, and that's going to give you two columns. That's going to give you, it'll give you x1 and y1, but I've already used that down below. And you just input the data here. So what you can see on my table, so down here in number 2, okay, so you see I have my x1, my y1. If you go and refer back to that previous data set, this is the data set. Okay, so 35, 5.88, 50, 5.99, etc., etc. That is the data from that example. Okay, and then ignore the third column for just a second. But if I go ahead and turn that one on, you can see right there we have all of the data points for this data set. Okay, so you can see we talked about it a little bit last time, but they do appear to have a more linear relationship to them. So what we can do is we can, since we're just trying to look at this first, we're not trying to actually find anything exactly yet. Let me just move this down here. Okay, so we're going to just play around with kind of some of these cool features on Desmos here. Okay, so we're just going to start 0, 0. So you can type in y equals mx plus b, and Desmos, of course, recognizes that as a line. Okay, so here's the line down here. And what we can do is we can change the slope and the y-intercept by just adding sliders to those values, right? So if I got rid of these two, notice Desmos tells me I can add a slider. I just select all, and then it's going to allow me to kind of play around with the m value, which is the slope. Okay, going from -10 up to 10. And then my y-intercept shifting up and down. I know it looks kind of weird. It looks like it's shifting left and right, but that's actually up and down that's shifting here. So this is kind of hard to see. Notice the scale is pretty offset on this. Right on the horizontal axis we're counting up by 50s, but on the vertical axis we're only counting up by 2s here. So let's play around with these values. So this seems pretty steep already, so I think we need it to be less steep than this. Possibly even less than that. Let me go ahead and shift up my b value a bit. Something like right around here. Let's try, let's see, 0.1, now 0.01. Ooh, okay. Now we're talking a little bit. The b value, maybe bring it down a little bit. Somewhere kind of like in there. Right? And at this point I'm just trying to give you kind of a good visual of what this line would look like. So you can kind of see that's kind of cutting through the middle of the data there. So, you know, our guesstimate would be the line, you know, y equals 0.01x plus 5.7 approximately. But luckily, Desmos has a feature for us where we can actually find the linear regression line, so that line of best fit. And what we need to do is type in, so down here on the bottom of the screen, you'll see we type in y1, and I'm using y1 because that's what's in the table up here. So this is y1 and this is x1. So we have y1, and then the little squiggle symbol. Okay, so that tells it to do a linear regression. M1 x1 plus b1. Okay, so this tells it the output variable is y1. It tells it the input is x1. And then I went ahead and called my slope m1 and I called my y-intercept b1. And when you do this, what happens is Desmos recognizes this equation, and it can tell you what the m and b values should be to make this least squares regression line most accurate. So you can see the slope it gives is 0.011553. Okay, so that's right in here at the bottom. And then the b value, the y-intercept, 5.52727, etc. And if I plot that line, there it is. So that is the least squares regression line. That is the one that is the best fit of the data. Now let's see, we weren't too far off, right? We have 0.001, so our slope was a little low, barely, and our b-intercept, our y-intercept was a little high, but to plot that, that's not too bad, right? We were just slightly off a little bit here. Okay, so anyways, you get the idea. But this is the least squares regression line. Okay, so we can use Desmos to plot this just using this function. So if you ever need to type this up, that's how you type it. Okay. All right, so let's go ahead and get back into the notes. We're going to come back to this in just a minute, so don't worry. Okay. Then they give a warning here at the bottom of the page. So remember, it's always important to plot the scatter diagram first. So you don't want to just go in and plot some linear regression line, because if the data is not linearly related or doesn't have a strong linear relationship, then there is no point in drawing the line, right? And the line would be useless at that point. So we need to do the scatter diagram first to make sure that it's actually worthy of drawing the line. Otherwise, we're just kind of wasting our time with that. Oops. Okay. Now we're talking about what is called residuals. So residuals are the difference between the observed value of y and the predicted value of y, or y hat. That is the residual, sometimes referred to as an error. Okay, so the residual, this is kind of what we would expect based on our line versus what the actual data point tells us. Okay, so let's predict the drilling time if drilling starts at 130 feet. Okay, so let's go back and look at Desmos. So now, ignoring the data points, so if we were going to predict, so I said here's my line, right, my least squares regression line. I want to predict how long the drilling will take if I start at 130 feet deep. So let's go find 130, right in, oops, there, 130 comma 7.029. So our prediction would be at 130 feet, drilling time 7.029 minutes. So that would be our prediction based on the behavior of the line. Okay, but in this case, we actually do know what the actual time is at 130 feet. So if you go back and look at the data, it says that the actual recorded, or I should say observed, the actual observed time is 6.93. Okay. So is this above or below what we expected? Well, this one would be below, right? Below average. Because the line would tell us that we would expect it to be a little more than 7 minutes, and this said it was a little under 7 minutes. So it's not a drastic difference, but it is a difference, right? It was not exactly correct. Okay, and then it asked us to calculate the residual for 130, so that I can show you on Desmos. This is another nice feature of the tables. So when you create a table and you put some data points in here, there's a third column, and as soon as you start plotting data points in here, it will ask you if you want to plot the residuals. And if you say yes, then it'll actually plot the residuals here for you in the third column, and that's what this is. So this E sub 1, that is the residuals. And what I can do is I can actually plot that value, and if I scroll down a little bit here, you can see there they are. Those are all the residuals. So the residuals are telling us how far above or below the line our actual data points are. Okay, so you can see here we're below, below, above, below, etc. And that matches, right? These are all below, above, etc., etc. So you can see the data points, all the ones up here, match the shape of all the ones down there, right, in terms of their relationship to the line. So the one we're looking at is the data point at 130, so the residual at 130. On there it says negative 0.099, but if you look in the table, it's actually a little bit clearer. So the 130 row here is right there. So that's negative 0.099157112. So we got a pretty nice exact, or as close to exact as we need, answer for this one. So we get negative 0.099157112. So what does that tell us about what does the residual tell us about our data point? Well, that tells us the negative tells us that it was below the line, and 0.099, so 0.10, so about a tenth of a unit below the line, so not very far off, which is good. You can see on some of the other ones here, they're a bit farther away, right? So you've got some of the further ones like this one up here, That's 0.652, right? So that's over 0.6 units away, right? You've got 0.556, 0.544. So you got some further ones away. This one's actually fairly close to the actual line. Okay. So now when we're talking about slope and y-intercept, so in terms of just a line, the equation of a line, slope and y-intercept, right, slope tells us the rate of change, y-intercept tells us where it intersects the y-axis, right, the vertical axis. In terms of the context of these problems, right, with the linear regression lines, we can talk about what these actually mean in these contexts. So we would say the slope, which of course is calculated as rise over run, tells us how the data grows. So it tells us whether the data is positively related or negatively related, right? As one value increases, does the other value increase or decrease? And how quickly? Okay, so not only is the data growing up or down, but also how quickly is it doing that? Is there a very sharp, steep increase or decrease, or is it very gradual? In this case, we got a slope that was a little bit more shallow. So we have a positive relationship, but a very slight relationship, not very steep or drastic. Okay, and then the y-intercept. Right, this is also known as our initial value. So this, as it says, is the initial value. This tells us about where the data starts. So, and then the data can go above or below this, depending on the slope. Okay, so if we have, like in our example, we have a data set that is positively associated, which means that the data is going to be increasing, right? The line is going to have a positive slope, which means the initial value is actually the smallest value, right? In terms of greater than 0, right, as time goes on. But if the slope was negative, then the initial value, the y-intercept, would actually be the largest value, right? Because instead of the graph going like this, right here the y-intercept is the lowest value, the graph, if it was negative, would go like this, in which case the y-intercept would be the highest value. Okay, so that just depends from graph to graph. Okay, now one additional thing they want to warn us about. We can use the linear squares regression line to make predictions based on the values of these variables, but we need to stay kind of within the parameters or within the scope of the model. So if a researcher is using these to predict values that are much larger or smaller than the observed values, we say that they're working outside the scope of the model. Okay, so and then it gives the warning right here, red. Never use a least squares regression line to make predictions outside the scope of the model. Okay, because we don't know whether that regression, that linear relationship, continues outside of the data set. Okay, so we can use it to make predictions and try to understand what's happening inside that data set, right? So in our example, we're going from 75 up to 200. So if I wanted to try to predict the value at 136, right, I could go ahead and try to use the line to do that. But if I'm trying to predict what's going to happen at the value of 2000, right, that's way beyond the scope of our model. So we would need to get more data, make a better model, something like that to accommodate it. Okay. Then we get the correlation coefficient. So the correlation coefficient tells us how strong the linear relation is between two quantitative variables. So in other words, how good is our line? Okay, so how appropriate is our line? So if I have a bunch of data points here, so here's my graph. I have a bunch of data points that all kind of go like this, and I draw my line, and we say, wow, yeah, that line is actually a really good fit for that data set. Well, that would have a very strong correlation coefficient, okay, because the data points are very much linearly related. Whereas if we took a data set that was not so strongly related, so just kind of something like this, and then try to draw, a line of best fit, that would have a very weak correlation coefficient because it doesn't look like the line fits the data very well. Okay? So this is what the correlation coefficient tells us. It gives us a numerical value for how appropriate it is to have a least squares regression line. Okay? Now this is the calculation they give for R. We're not going to worry about that because, as you can see, this calculation can get really ugly really fast. So we're just going to be using Desmos for it, and I'll show you that in just a second. Okay, but here are a few properties of it. So go through these really quick. So property 1, R is unitless. It is always between -1 and 1, so this is a good thing to remember. Positive values of R correspond to positive relations. So positive values, positive relations. Negative values mean negative relations. Okay? So the closer R is to +1, the stronger the positive correlation. And when R equals +1, there is a perfect positive relation. And then the closer it is to -1, the stronger the negative relation. When it is -1, there is a perfect negative relation. And the closer it is to 0, the less of a linear relation that there is, either positive or negative. Okay, so R will always be between -1 and 1. The closer it is to 0, the weaker the relationship. Okay, but the closer it is to +1 or -1, the stronger the relationship. Right? So like in the examples I was just drawing. So, this data set here, right, this would have a positive relationship, probably very close to 1 in that relationship. Whereas if I drew, something like this, that would have a very strong negative relationship. So that would have a value pretty close to -1. But if I drew something like this, like I had earlier, kind of all over the place here, and I try to draw a line, that's going to have a value pretty close to 0 because there's very little correlation there between those values. Okay. So determine, in this next example, the linear correlation coefficient for this example and interpret that R in the context of the drilling depth and the time. Okay, so let's go back to Desmos. So this is a great thing about Desmos, is it gives all these values to us. So if you notice here, you can actually get the correlation coefficient by typing in the function. So CORR is actually the correlation function. And you can correlate your first column and your second column together. But what you can actually do is when you make the regression line, so down here, so the y1, right, squiggle m1 x1 plus b1, notice under the statistics right here, there is R. So R equals 0.7728. That is the correlation coefficient. So that is R. Okay. So Desmos, if you just plot this scatter plot and then you create the linear regression, it's going to just give you the correlation coefficient, which is so helpful that we don't have to calculate it by hand. Okay. So we get 0.7728. Alright, so we get R equals 0.7728. So what does this tell us about the relationship between drilling depth and the time it takes to drill 5 feet? Well, this value is positive. Okay, so it has a positive correlation. So positive linear correlation. And because this value is so close to 1, right, that's only 0.23 away from 1, I would say that this is a strong positive linear correlation between these two variables. Okay, so that means between the relationship between drilling depth and the time it takes to drill, I would say that there is a strong relationship, a positive relationship between those two. Okay. Then we have the coefficient of determination. So the coefficient of determination, this is where we actually get some interpretation here. So this is r squared. Now they call it big R squared, but it actually is just, computation-wise, is just the same thing as squaring the correlation coefficient, so little r. So we're going to have, so big R squared, we compute that by just getting little r squared. So that's how we do that. But big R squared, so the coefficient of determination measures the percent of total variation in the response variable that is explained by the least squares regression line. So it measures how well this line describes the relationship between the two variables. Okay, so it measures how well it describes this relationship. So, because it's being squared, it will always be between 0 and 1, so it'll never have a negative value. And if it's closer to 0, that means we have 0% explained by this model. So that means it's a bad model, right? Our line is not doing a good job of explaining our data. But if we're closer to 1, that's 100% explained. That means that would be a very strong model. It would have a lot of explanatory power is what we call it, but be very, very strong. So determine the coefficient of determination, r squared, for this example, and interpret. So, in this case, we can again refer to Desmos. So right there, back above where we had r, there's r squared. So that's 0.5973. You can also just square the value, because that's all it is r squared. So we get r squared is 0.5973. So what does that tell us? It tells us we have about 59.73% explanatory power. Okay, so that tells us how strong and how well the line describes the data set. So basically, we're almost at 60%, so that's pretty good, right? Certainly, it's closer to 100% than it is to 0, right? So I would say that this line does a fairly good job of explaining this data set, right, and resembling what's going on in the data set. Okay. So there we go. It talks about squaring the correlation coefficient. Now, this method, and this is why they mention this kind of in a box here, but squaring that linear correlation coefficient to obtain big R squared works only for the least squares regression, linear regression model. So this method does not work in general. So it only works when we're dealing with linear regression. So if we do any other type of regression, this wouldn't work if there was any other type of relationship. But this is what we're doing right now, so we can go ahead and use that to our advantage. Okay. And then the last big discussion point here for this section is the idea of correlation versus causation. So the idea that correlation is not causation. Just because two things are correlated to each other does not mean that one causes the other. Okay? Now, in real life, there may be some causal relationship there, but we are not able to prove that simply by running this type of test. Okay? Just because two variables are strongly correlated to each other does not mean that one had to cause the other, right? It could be that one caused the other, but this test does not tell us that. Okay? There is a very big difference between correlation and causation. So let's look at a couple examples just so you get the idea. So according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.940. Does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? So, just by looking at the data, right, so we have the correlation between female population with bachelor's degree and the percentage of births to unmarried mothers. That's a pretty strong correlation, 0.94. So that's 90. That would be, if we were to square that, right, that would be a very, very strong correlation. But does that mean that the higher percentage of females with bachelor's degrees causes the higher percentage of births to unmarried mothers? Not necessarily. Okay, so that's an important thing here, is not necessarily. Okay, so just because the two correlate does not mean one caused the other. Okay. And even just running statistical tests, this is where you get a lot of like false claims and faulty claims based on data. They say, look, the data says this, therefore, this caused this. The data is not able to create causation. So if somebody's ever trying to say, this data explains why this causes this, that's not the case. It just means that the two are related, possibly. They correlate to each other. But we even know in regular studies there could be confounding, right? If you throw away back to chapter 1, there could be other factors there that maybe cause both of them, or maybe are related in some other way. So we cannot make conclusions like that based on data. So correlation, not causation. So, and again, when data is observational, we cannot claim a causal relationship exists. We can only claim causality when the data are collected through a designed experiment. Okay, so a designed experiment, right, would be something where you control all the factors, and then you have a definitive statement on, we had everybody in the same room, we gave the same tests, and we only changed this one thing, right, manipulated one variable, and it caused this change, right? In that case only, we could talk about that, right? And then, of course, we talked about, right, the lurking variable, right, and confounding that can occur. So here's one more example. It's kind of an interesting one. So ice cream sales and crime rates actually have a very high correlation. Does this mean that local governments should shut down all ice cream shops? So hopefully you can tell me the answer to this one right away is no. They should not do that. Just because those two are correlated for some odd reason, clearly, we can use our common sense on this one and say, no, clearly those have nothing to do with each other. But this is the type of argument that people make, is they say, well, these two are highly correlated, so we better change something about one in order to prevent the other, or in order to help the other. But unless you have a designed experiment, just because there's a strong correlation does not mean that one caused the other. So that's it for section 12.3. When we come back in 12.4, we're going to start looking at a type of hypothesis test that we can do to look at significance of linear relationships. So we'll be back with that in just a little bit.